Welcome to Digital Learning on Steel Structure. Presently we are discussing on design of roof truss, in which we have completed the load calculation of roof truss, design of purlin. Presently we are discussing about design of truss member. In the design of truss member, the member designs are categorized into three categories. One is top chord, the second one is bottom chord, the third is web members. When I am seeing the design force on the members, the top chord members as well as the bottom chord members are subjected to higher intensity compared to the web members. Therefore, built-up sections are essential for the top chord and bottom chord. For web members, if the members are longer and subjected to compression, in that case, and also the member force is also relatively higher, then in web members also built-up sections are essential. Here, when I am taking the fan members, maybe single sections are sufficient. Today I am going to explain about the design of top chord member. In my earlier live session, I have explained about the top chord member design. To recap the design, I will add some points. Here, I consider a top chord member subjected to loads of two nature. When the top chord is subjected to dead load and live load combination, the maximum force expected is 180 kN, but the nature of the load is compression. When the same top chord, when it is under dead load and wind load combination, the nature of force is tension of magnitude 100 kN. Therefore, for all truss member has to be designed for the various load combination. Here, comparing the two magnitude, the compression magnitude is predominant. Therefore, the top chord is to be designed for compression and check for tension. In the last live session, I have explained the design of compression member. In this lecture, I am going to give some additional information about the capacity check against tension. That is, the same cross section what is designed for compression, which is nothing but two angles ISA 70 cross 45 and cross 80 to be placed in this way, that is on either side of the gusset plate as the top chord member under compression. The same member going to be checked for the tension, the reversal of force. To check against tension, we need to know the connection details. Therefore, the first thing we have to do is the number of bolts required for the member. So for which I am considering the bolt detail are like this. That is, the size of the bolt will be 20 mm diameter of grade 4.6. I am going to calculate the bolt strength of the assumed 20 mm dia bolt. I am going to calculate the bolt under shear. So we know that this is an expression to calculate the shear capacity of bolt. Since it is a built-up section having two shearing, this is the point I am going to connect the two member to the gusset plate. Therefore, to calculate the bolt strength, the shear failure plane will be 2 in number. Therefore, I am calculating the shear capacity taking two shear plane. One I have considered on the solid cross section, another plane on the threaded cross section. Therefore, I reduce the area into 78%. That is, I am calculating the total area multiplied by 0.78. That is the threaded area I am calculating. So by which I got a capacity as 103.31 kilonewton. So to ascertain the bearing capacity, I have to use this expression which is given in IS 800-2007, in which to estimate the KB, I have to assume the pitch and edge distance of the bolt. Here I consider the pitch will be 75 mm, the edge distance approximately half of the pitch. In this problem, I am assuming the pitch as 35 mm. Therefore, I calculate the KB. This is the smallest value among the 4 values. So taking this as kb, I am calculating the capacity, and the bearing capacity of bolt is nothing but 67.84 kilonewton. If this is the value, by comparing the shear and the bearing, it is very clear that the bolt capacity is nothing but smallest of the two. Therefore, here the bolt capacity is governed by the bearing capacity of the bolt. Now we will calculate the number of bolts required for the tension member. The tension member is subject to a tensile force of 100 kilonewton. The capacity of one bolt is 67.84 kilonewton. Therefore, the number of bolts required is nothing but 1.474. Approximately it is equal to 2, but here I am taking 3. Nothing wrong to take it 2, but in this problem I am assigning the number of bolts as 3. After knowing the connection, we'll go for the capacity check under tension. As per the IS 800 section 6, we know that to check a section against tension, we have to check the capacity against 3 criteria. One is yielding of gross cross section, rupture at critical cross section, and block shear failure. So first I'll take the gross section yielding, where I'm taking the total cross section of my angle section. Here, since I am using a built up section, the area is a total area, and I'm multiplying the stress, I'll get the capacity as 390 kilonewton. Coming to the rupture at critical cross section, so this is an expression. So this is for rupture capacity of an angle section. Here I'm using two angles back to back of a gusset plate. So I'm taking one angle, I'm calculating the capacity of one angle, then I multiply by 2 to get the total capacity. So here in this single angle section, the capacity is calculated by adding the capacity of connected leg and unconnected leg, that is outstand leg, where you have to calculate the shear lag effect. So to calculate the shear lag effect, you have to know certain dimension parameters. So this is the expression of your shear lag effect, for which you have to know so many parameters, where this W is nothing but amount of outstand. Here in this tension member arrangement, where the 70 mm leg is connected to the gusset plate, so the 45 is going to be act as a outstand. So here the W is length of outstand is nothing but 45 mm and the thickness of the outstand. This is about the yield and ultimate stress of your angle section, where BS is nothing but outstand leg, which is nothing but the outstand plus the back angle distance. The outstand is 45. The back angle you can get it from SP6 part 1 in the page number 168. For angle length of 70 mm, the back angle distance is 40 mm. And since you are calculating the mean line of this outstand length, you are minusing by thickness 8, because here half the thickness, here half the thickness. So you'll get the outstand length will be 77. Length of connection is nothing but the distance between the extreme bolts, where there are 3 bolts are provided. Therefore, the length of the connection is nothing but 75 plus 75. You will get your length of connection will be 150 mm. So if you substitute these values, you will get the value of beta. In addition to beta, we also know what is the area of the connected leg and the area of the outstand leg. Here, ANC is nothing, net area of the connected leg, where the connected leg is 70 mm, where bolts are going to be used. Therefore, some bolt holes are placed in the connected leg. Therefore, I am calculating the net area. So, this 66 is nothing but mean line of the connected leg, where 70 mm minus half the thickness, that is this to be deducted. You will get length of the connected leg into the thickness. What is this? This is nothing but bolt hole. So here, if I am taking a particular cross section where I have only one hole, therefore I am deducting one hole diameter. So this is a net length into a thickness. You will get net area of the connected leg. Coming to the outstand, so the outstand is nothing but 41 into 8. So you will get the gross outstand area. With these values, you calculate what is the connected area, outstand area and beta value. So substituting all the parameters here, you'll get the beta value will be 1.266. Then you take the expression and substitute your net section rupture and gross yielding put together. You will get what is the capacity of one angle, that is 198.285 kilonewton. Basically, you have two angles placed on either side of the gusset plate. Therefore, you multiply by 2. You will get the total capacity under rupture will be 396.57. The third criteria is block shear failure. You already know that it is a double angle placed on either side. So, I am going to calculate the capacity under block shear. So, here again I am taking only one angle capacity and multiply by 2 later stage. Here you have to calculate that block shear failure. According to the code, the block shear failure is estimated by this failure plane. Here under the load, under this plane, the angle undergoing shear, and this plane, the angle undergoing tension. So under the shearing plane, the angle may subjected to yielding. At that time, in the tension plane, it is subjected to rupture. Vice versa, on the shearing plane, it may be under ultimate. On tension plane, it may be yielding. These are the two combinations we use to calculate the block shear capacity of the angle. So for which I am calculating what is the areas, the corresponding areas, where AVG is nothing but gross area in the shearing plane. That is, forgetting about the whole diameter, you simply take the solid cross section. Therefore, here I am calculating the exact length of the shear plane into the thickness. I'll get gross area along the shearing plane. Same plane, if I also need the rupture. For the rupture, I need the net area. Therefore, this is the net length into the thickness, where this is the total length minus. So, how many diameter of the hole going to be in the particular plane? So here the complete diameter, here again complete diameter, here half of the diameter. Therefore, I am deducting 2.5 whole diameter from this length to get the net length. Into the thickness, you will get net area along the shearing plane. Similarly, on the tension plane, here gross area means, so this is my 30. How I can get 30? I know that for the 70, the back angle distance is 40, the remaining length is 30. Here I have to take this length will be the tearing length. Along that length, the gross area is nothing but 30 into the thickness of the angle. So I'll get gross area along the net plane, some tension plane. Here net area along the tension plane is nothing but this length, where half of the bolt they are going to be not going to offer resistance. Therefore, you have to detect it. Net area you have to calculate. So 30 minus 0.5 times 22, where 22 is a bolt hole dia, into 8, you will get the net area along the tension plane. Using this, you substitute in this expression. So in this expression, here we are assuming there is a yielding happen in the shearing plane, rupture in the tension plane. Here vice versa, ultimate stress in the shearing plane, yield stress in the rupture plane. So taking these two extreme conditions, you are calculating the capacity of the angle, and it was found that among the two, this will be the governing value. So I am taking that value multiplied by 2. Why it is 2? Because here we have used 2 angle as the tension member. Therefore, the capacity against block shear is 463.594. That means if the load exceeds this value, then the section will fail in block shear value. So from this calculation, we came to know that the yielding capacity is 390, rupture capacity is 296, and block shear capacity 463. The lowest of the three is going to be the governing capacity. That is, here it was found that the cross section capacity is governed by yielding of gross cross section. The capacity of tension member is found to be 390 kilonewton, which is greater than the force acting on the cross section. Therefore, the given section is safe against both compression as well as tension. Thank you.